So now that we know about these new kinds of complex numbers, we're going to talk about doing some operations on them. We're going to start with adding them, adding complex numbers. Now the way we add complex numbers is just an invention by mathematicians. They found that this way works well and has a lot of properties that we can use. So let's first look at our two complex numbers. Remember, a complex number has a real part and it also has an imaginary part, and we're going to add them. So a plus bi plus c plus di. And a, b, c, and d are all in the real numbers. This e means elements in the real numbers. So these are all real numbers, and this real number is attached to this I, which makes this whole number imaginary. So when we add them, it's pretty simple actually. We're just going to take the real part and add it together, and the imaginary part and add it together. So let's look at a specific example. So 5 plus 2i plus 6 plus 4i. So we're going to take the real parts, 5 plus 6, and that gives us an 11, and then 2i plus 4i, which gives us 6i. So now let's look and see if in this particular case, in this specific case, if addition of these two complex numbers is commutative. Commutative is when you add the first one and the second one and it gives you the same result as the second one and the first one. And it actually doesn't even have to be two. It can be lots of different numbers. Now we know this is true for our real numbers. If we add 3 plus 1, that's the same thing as adding 1 plus 3. But let's look at this specific case. So our specific case is 5 plus 2i plus 6 plus 4i, and we got 11 plus 6i. Now let's reverse them, and let's add the 6 plus 4i plus 5 plus 2i. So we do the same thing. We're going to do 6 plus 5, and because real numbers, we can add 6 plus 5, and that's the same as 5 plus 6. That gives us an 11. And then we'll add the imaginary part, 4i plus 2i, and that gives us, adding the imaginary part, 4 plus 2, it's just 6i. So in this case, yes, adding is commutative with our complex numbers. Now let's look at a more general case, a real algebra case. So it may have worked for that instance, but we can prove it's going to work for every complex number. And the way we can do this is we're going to use variables in place of those numbers. By doing that and saying that these variables belong to our real numbers, we can show this is true for all of the complex numbers. So we're going to use algebra to show complex addition is commutative. So our first number is a plus bi, and our second number is c plus di. So we have to also remember that a, b, c, and d are all real numbers, and we know that addition is commutative with real numbers. Let's go ahead and add them. So a plus c is just a plus c, plus bi plus di. So plus bi plus di. Now we can factor out the I right here, and we have a plus c plus b plus d times I. If we were to distribute that I, we would get right back up here. So now we have b plus d, which is a number, a real number, because we have two real numbers added together, and another real number here. So this is our answer to the algebraic two numbers we're calculating there with our operation. So now let's look, let's reverse them. Let's do c plus di plus a plus bi. All right, so we're going to do c plus a, and we're going to do di plus bi. So we get di plus bi. Again, we're going to factor out that I. So if we factor out the I over here, we have c plus a plus d plus b. Now, here's where we need to remember that real numbers are commutative, because all of these are real numbers. So a and c are elements in the real numbers, and so are d and b. So because this is a real number right here, we can say that's the same as a plus c. And the same is true here. D plus b is the same as b plus d because real numbers are commutative. Now let's look at subtraction, which is a lot like addition, actually. And we're going to look at subtraction of complex numbers. So let's give a specific example, 5 plus 2i minus 6 plus 4i. Works kind of the same way. We're going to distribute this negative to our complex number. So let's just rewrite that after distributing that negative, kind of like polynomials when we were subtracting different terms in our polynomial and different polynomials from each other. So 5 plus 2i plus negative 6, distributing that negative, minus 4i. And now this looks just like our addition of complex numbers. So we can add 5 and negative 6, which gives us a negative 1. And then we're going to add our imaginary parts, 2i plus negative 4i, and that gives us a negative 2i. So this is the answer to my subtraction of these two complex numbers. Let's try another one with a few more negative signs in there. Let's say we have negative 6 minus 3i minus 5 minus 4i. So negative 6 minus 3i plus, let's distribute that negative, negative 5 plus 4i. We have that negative and negative, which gives us a positive right there. 4i, and now we can just do our addition. So we can have negative 6 plus negative 5, which gives us a negative 11, and negative 3 plus 4, which gives us an I.